Hello teammates, it's Mr. Nitty coming to you with the solution to yesterday's FRQ. I gotta work on my lighting. You got a roller coaster cart. We've done problems similar to this in the past. It's got a little uniform circular motion twist. Again, as you approach these problems, the first thing you do is read the whole question, then identify what kind of problem it is. Again, while you may see a pendulum, not this problem, while you may see a pendulum, and it may be a conservation of energy problem, might have nothing to do with simple harmonic motion. So you got to read the problem, and then you've got to work to solve it. Right? This is in math class where you're just going to repeat a pattern. You're going to have to think through. Good. So you got a roller coaster cart, starts there. We're going to look at position A. Use College Board's scheme. If they say that's point A, you're going to call it point A. Negligible friction. Initially, we're going to add friction here in a bit. I think we're getting a mass, initial velocity, a height, and a radius of that circular arc. So that should clue you that you're looking at some kind of UCM. We're going to calculate the speed. We're going to draw a free body diagram. We're going to look at the magnitude of the force the force normal. Magnitude of the force of the track on the car. So recall that back in October, we talked the force is an interaction between two objects on the feeler by the dealer. What's the cart feeling from the track? We're gonna calculate what it takes to bring the car to rest at point A, and how to modify the track design to cause the car to lose contact. So let's go. FRQ 8. Type problem: energy conservation with a uniform circular motion twist. I think if you write that, it's going to keep you focused. So 1 point, identify the conservation of energy. State that. Easy money. Don't throw away a point. And again, teammates, I'm not going to say it's tricky. College Board doesn't tell you what the points are, right? It's not like a rubric. I think my own view is this constant use of rubrics has ruined us because we just look to fill in the blanks. You're not going to have a rubric. So energy conservation. You're going to write your conservation energy equation. You've got both forms at the top of the track. The cart's in motion, plus it's got some position energy, and the next part it's got some position energy, and it's still moving as well. Now you can. I'm going to show you a key for one way. You can do it like much of physics. There's more than one way to do this. There we are. So I'm going to show you how I solved it using this as my arbitrary zero. You sure can use this as your arbitrary zero as well. Well, that looks like they're the same height, but we know they're not. Just a 0.1 meter difference. I didn't do too good a job drawing that. Either way works. But you got to establish that arbitrary zero. I'm going to show you one way with the arbitrary zero at the ground level. Conservation of energy, then put in your variables for that. You don't have to write this and then write it again to cancel your masses. You can write it once and then cancel your masses. Isolate your variables. That's almost always a point. To go from here to there is almost a point. So if you go from here to there, you might lose a point. And then you're gonna square root it. I recommend you do this. They may let you go from there to there. I recommend you go here and then there. Always isolate your variable. Then you're going to. There's a second page of this somewhere. There it is. You're gonna solve. Again, 10 meters second is fine. When you get your exam, if it says something different, it says use 9.8. Easy money. It's good. You're gonna solve about 2.12 meters per second. It's a toy cart on a toy track. If you got 21 meters a second, think about it. That's that's like a fifth of a football field in a second for a toy car. It's not going to be like that. If you got like 0.02 meters per second, that's pretty darn slow. So to do that last step, it's good. Part B, we want to look at our free body diagram. 2 points. One for the normal force, one for the force gravity. If you draw an extraneous force, if you draw something like this, you're going to lose a point. Right? Yes, the car is moving in that direction, but there's no unbalanced force in that direction. The change in velocity is caused by the change in energy. And so this is just my note to you. You're going to draw your center-seeking force is towards the center. So that's going to be greatest. You know that the weight doesn't change. So your force normal's got to decrease. I'm just showing you so force centripetal is going to be force gravity minus force normal. So force normal is going to be force gravity minus force centripetal. I recommend you do that. Don't try to memorize a pattern. Again, this is not math class. Don't try to memorize a pattern. It's going to get you into trouble. This one a lot longer than I thought it. I thought it only had 2 pages. Let's go. Calculate the magnitude of the force normal. You don't have to redraw your free body diagram. I did that because it was on the previous page. You're gonna say I'm gonna calculate the magnitude of the force normal. I'm gonna use centripetal force. I know my force normal is gonna be force gravity minus force centripetal. You can walk the dog from the part above. Then they like to see you do this. They like to see you do that. Force normal equals force gravity mg minus force centripetal. This. They like to see you do that. And then put your variables. Your values in, and then solve. It's good. Walk it step by step. Teammates on the AP exam. So I'm not saying I'm anybody special. I'll work your answers back. I'll take. That's why it takes me a while. I'll work your answers and see where you made a mistake. They are not going to do the math for you. So if you do this and you skip this step and you write 1.63 and it's a calculational problem, you might not get that point. But if you show them step by step, they can say, all right, that's an easy math error. We're not going to worry about that. It's good. Does it make sense? They're not going to. They spend a minute on your question. They're not going to go back. They're not going to go back and redo your math. Part D. Talk free body. Let me talk free body one more time because I talked about. Oh no, that's all right. Never mind. Wrong problem. So much going on. Order the car to stop at point A. What happens? Another energy conservation. Car's velocity 2.12 meters per second must have enough friction to bring it to zero. We're going to write friction equals kinetic energy. It's actually right. Friction is doing negative work. So you could start that with Ke minus work friction equals 0. That's probably smarter. Then you put your variables in. Then you're gonna solve. Use that negative sign, right? Because friction is doing negative work, right? So that negative sign is coming from there. I'd put the negative sign. Are they going to take a point away for that? Maybe not. But you know that friction is doing negative work. And if you want to put some words in there, whoops, I have that on screen. There you go. If you want to put some words in there, that's all right. All right. Last part, headed for home. Explain how the track design to cause the car to lose contact with track A before descending down the track. We've done one like this before. It's a centripetal motion problem. For the car to lose contact at point A, there must be no normal force, right? So it's in free fall. If it's not in contact with the road, the only force acting is force gravity. It's in free fall. It's good. It's good. You'd have to modify the track by making the radius smaller, such that, so you could either, so they're asking you how to modify the design. You could do a couple things. You could raise the point where the cart started at, so it has more velocity. You'd explain that, how the car would have more velocity. And or you could tighten that radius, so you get a lower R. I'd walk them through the equation though, on what you're going to manipulate. This one's not asking you to solve anything, but you would want to show that your, because masses are going to cancel, your centripetal acceleration, right? Velocity squared over r, centripetal acceleration, is going to be greater than g. So there's a couple ways to do that. You can raise the hill. You can decrease the radius. A couple students on the prior one said, like, put oil on the track. They're really not looking for that. They may let you get away with that, right? That would reduce your friction. But they're really looking for a physical modification in terms of conservation of energy. They may let you do something like that. It's good. All right, teammates. Have you a great day.